Greetings everyone. In this video we'll talk about spherical coordinates. Now, spherical coordinates are a way of representing locations of points in 3 dimensions, just like the cylindrical coordinate, and we need 3 different numbers to identify the location of a point that we're interested in. Let's say that point is P, and R is defined as the distance between the origin and the point P. This particular distance is R. Next, we have the polar angle theta, which is the angle subtended between the positive z-axis, this is the positive direction of z, till this line segment connecting the origin to the point P. And then we have the azimuthal angle phi, which is the angle subtended between the positive x-axis to the projection of this particular line segment connecting the origin and the point on the xy plane. In particular, in this figure is this dashed line that I just covered. So this particular angle is then phi. And note that in some books they use different conventions. Different letters can be used instead of r, theta, and phi. Also, theta and phi might have different roles. That is, phi can be used for polar angle, theta can be used for azimuthal angle. But in this video and the following video as well, we will use theta as polar angle and phi as azimuthal angle. Now we have some constraints on both r and phi. That is, r is defined, since it's defined as a distance, r is always greater than or equal to 0. If the point is at the origin, then r equals to 0. For every other location, r is positive, it's greater than 0. And for theta, we have the constraint that it's always greater than or equal to 0. It's equal to 0 if a point lies on the positive z-axis, and it is less than or equal to pi if it lies on the negative z-axis. For phi, there is no such restriction like this one. Now let's see how we can plot a point such as this one in spherical coordinates to have an idea of how spherical coordinates work. So here we know that r equals to 2, theta equals to pi over 3, and we have phi equals to pi over 4. So let's start with phi. So phi is the angle will start from the positive x-axis and will go till, if this is pi over 4, we'll draw out a projection line. Next we'll have pi over 3 as the the polar angle from the positive z-axis. So if this is pi over 3, then the line which has a distance of 2 starting from the origin. So if this distance is 2, it should be straight. Sorry about the diagram. So if this distance is 2, this is where our point 2 pi over 3 and pi over 4 lies. And yeah, directly below it this is the projection of this line segment onto this onto the xy plane. This will create a 90-degree angle, or a pi over 2. So this is where our point lies. If we call it P lies over here. So now let's move on. So if we have a point P in spherical coordinates, so how can we turn it into Cartesian coordinates? So it's actually quite easy. We'll use this particular image. We can use this. So here we have r, right? So how can we let's get rid of this green stuffs. So how can we get this particular dashed line? Turns out it's quite simple. So this is actually a right triangle, right? So we can use simple trigonometry. So this is an alternate angle. So this is actually theta, and this means that this dashed line is none other than r. This is a right triangle, right? So you can use trigonometry, r sine theta. Now since now we know that this is r sine theta, this is also another right triangle, and this angle is phi. So this means since this angle is adjacent to, is touching this hypotenuse, so this means this particular part must be equal to, which is the x coordinate. This r sine theta is my hypotenuse, so it's r sine theta cos phi. So we write that down. This means that x equals to r sine theta cos phi. Next we will have, so the other side, which is the y coordinate, if this is, and because this is actually a rectangle, this dashed line is the same thing as this y coordinate. So we know that this is the hypotenuse, r sine theta, and the opposite side to this particular angle is this dashed line, right? So this is the y coordinate, so this is going to be r sine theta, the length of my hypotenuse, times sine of phi. Let's move this thing so it's going out. Okay. So this particular y coordinate is going to be r sine theta sine phi. So we have y equals r sine theta sine phi. Last but not least, we now have the z coordinate. Find the z coordinate is the simplest of all. This is already a right triangle. We have the adjacent angle to the side that we want. Let's move this out of the way. So this is my z coordinate, and this is just since it's touching this angle, so this is going to be r cos theta will be my z. Next, if we have a point P in Cartesian coordinates, how can we turn it into a spherical coordinates? And this is very simple as well. So r squared is defined as x squared plus y squared plus z squared. Now this is where a major difference between cylindrical coordinate and spherical coordinate lies. R squared is not just x squared plus y squared, but also plus z squared. And this is how we will determine r. The next thing we should do is determine theta using z equals to r cos theta. Since we already have z from the Cartesian coordinate, once we have theta, we can use either this equation x equals to r sine theta cos phi or y equals to r sine theta sine phi with regards to which quadrant is my point lying in, so that we find the correct angle for phi. Now we'll just try to find the volume element for the spherical coordinates. It's quite simple. Imagine a very small cube-shaped thing is drawn with an infinitesimally small volume. So we'll want to find this volume, and we'll call this dv. So in the direction of r, we have a very small increment, or just a small differential element in the direction of r. We'll call this dr, this particular line. Next, we want to find the small differential element in this green side of my cuboid. Now note that this is just the angle subtended between r and r, this particular very small angle in the direction of theta, which is why it will be called d theta. You have d theta over here. Now we already know that this particular arc length must be equals to r times the angle, if angle subtended between these two arcs, so this two radius, so we have r d theta as one of the sides, so we have r d theta. Next we have the blue side. The blue side, this one is actually the same thing as this one. So we'll look at the xy plane because it's cleaner over here. So we know that the projection on the xy plane is r sine theta, as we've shown here, that this particular thing is actually r sine theta. So we have r sine theta here. Now we move a very small angle phi, so we call that d phi. In the direction of phi we move a very small angle, so we call this d phi, and this is a circular segment, so this other side is going to be r sine theta as well. This arc length is going to be r sine theta, the length and the radius times the angle, so you've got r sine theta times d phi. Now we have all three sides of my cube. I can find the volume element, so let's just do this once for all. One of the side is dr, the blue side is r sine theta d phi, and the green side is r d phi, r d theta, sorry. Now all we need to do is multiply these three things. Now the limits of the calculus will allow us to use the volume of a cuboid instead of trying to find the volume of an irregular shape. So these things are so small that we can use this. Now we take one of the side is dr, the other side is r sine theta d phi, then we have r d theta. Now, usually we will do the r integral first, so the standard way of writing this is we take this 2 r's, we get r squared, then we have sine theta left, sine theta. Now we have since the first integral we'll do is r, so we have dr. The second integral we'll usually do is theta, so d theta. Then we finally have d phi, the last integral we'll usually do. So this is my volume element, dv equals to r square sine theta dr d theta d phi in spherical coordinates. Next, if we have any solid defined, solid E, which is defined by a set of points in spherical coordinates, we can write it as, in spherical coordinates it will have points r, theta and phi, where if we have if our theta is bounded between alpha and beta, where alpha and beta are some constants, our phi is bounded between some constants c and d, and our r is actually bounded between a function r sub 1, let's call it r sub 1, which is a function of theta and phi, and r sub 2, which is also a function of theta and phi, which is likely to be greater than r sub 1 for all the points. And any region satisfying these three inequalities will define a solid in spherical coordinates r, theta and phi. Then we can say that if we have been given a function in, let's say, Cartesian coordinates, because we'll often convert Cartesian integrals into spherical integrals due to some spherical symmetry. So let's say we are doing the triple integral over the solid E. Then we'll convert this into these three limits. So the r limit is from r sub 1 theta comma phi, and then r sub 2 theta comma phi, and our phi is from c to d, theta is from alpha to beta. I've written in this order so that the order at which I'm doing the integration is obvious. Now we have our function, we need to change this, right? So x is r sine theta cos phi. Now we'll do y is r sine theta sine phi, and then we'll do z is r cos theta. The volume element is r square sine theta dr d theta times d phi. So this is how we will do a triple integral from Cartesian coordinate to spherical coordinates.